And so the intention is to review some issues on equations and stoichiometry of chemical reactions and solutions. What can you calculate from a chemical reaction? In the handout that I gave you, you should have a page in there that has that title to it. What can be calculated from a chemical reaction? Solution preparation, and finally solution phase stoichiometry. And I gave you some pages today on the handout that will support that last topic. Chemical equations and reactions. When we talk about chemical equations, most of you will recognize the fundamentals of its structure. Reactants go to products. And as with all natural events in the universe, it has a balance of mass and charge and energy and so forth, which means that the sum of the mass of the reactants equals sum of the mass of the products. And it's self-explanatory from a couple of points of view. One, grams. If you add up the grams of reactants, it equals grams of products. But one that you want to be certainly aware of is in moles, the concept of moles. So equations, stoichiometry is based upon the mole concept. The coefficients of the balance equation are moles, and those are always what we call the proportional relationships in a chemical equation. And represent proportional relations. For example, if we use a simple equation, 3H2 gas plus N2 gas goes to 2NH3 gas. Of course, it's balanced by the coefficients in the subscripts relative to mass and charge for the substances given. But what you want to be able to understand is the coefficients are moles. That is, 3 moles of H2 gas is involved here, 1 mole of N2 gas, and then 2 moles of ammonia is involved in this equation. And what this ultimately means in the understanding of mass-mass balance of the equation is this being the lowest whole number ratio of coefficients represents what we call the standard equation. Our smallest whole number ratio. And that's at STP conditions are 0 degrees C and 1 atmosphere. So when you reduce it to the smallest whole number ratio of coefficients going across any equation, turn the lights on here. That is the standard equation, and whether anybody says so in a problem or not, you are to assume it is 0, 1 atmosphere. And then there's a thermodynamic standard which involves 25 degrees Celsius, and that's something else we'll get to in the future. But what this means is that you can scale the equation up by mass, and you can cut it in fractions by mass. So if you need to, you can double the times 2, gives you 6H2 gas plus 2N2 gas goes to 4NH3 gas. Or you can go to fractions, say cut it in half, and you can have 3/2 hydrogen, 1/2 nitrogen, going to 1 mole or 1 ammonia. So these are possible in the working of chemical equations, in that these are ratios. If you always use 6 moles of hydrogen, and you'll need 2 moles of nitrogen to produce 4 hydrogens. But these are relative equations to those coefficients, but they're not standard equations. So this is the only one that's a standard equation. So the point in this first note is that, well, what is the chemical equation, and what's its foundation? It has to do with mass, and that's why it's used, because it provides a mechanism from which you can predict outcomes using certain amounts of reactants, or determine how much reactant you need to produce a certain outcome. In the simplest form, chemical reactions are classified in 2 forms: oxidation reduction and metathesis. The issue with oxidation reduction reactions is that in the process of oxidation reduction, the elements undergo change in oxidation state. And this is also known as redox reactions. There is a very specific method of balancing oxidation reduction equations, and I think I put that procedure in the handout I gave you this morning. It's this, and if you will turn in that handout that I just gave you, let me find one that's not so gnarly. I'll use something a little bit simpler. We'll go to that in a few minutes when we get to those kind of reactions. Something like magnesium as a solid plus hydrochloric acid in an aqueous medium, you'll see this eventually, it will produce magnesium chloride in aqueous medium plus hydrogen gas. And that, well, in identifying the oxidation states of the elements in that reaction, you'll see this one, of course, is neutral, which is element in its basic standard state. Elements in basic standard state are what are used in compounds, are used in chemical reactions, as in molecular reactions. So I'll bring that up later on. But here's hydrochloric acid. Chloride chloride's in group 7, so it's typically a -1 charge. Hydrogen is a +1 charge. Add them up, you get 0. Okay, and then you go over here to chloride. It's still a -1 in this one, times a -2. And you don't need a magnesium, though, assumes a +2 charge. And hydrogen goes to basic standard state, 0. And so how do you know it's in basic standard state? Well, if you haven't seen this before, I'll show you. The basic standard state diatomics are nitrogen, oxygen, fluoride, chloride, bromide, and iodide. This relationship says 7. There's 7 diatomics. Hydrogen is one of them. You just have to remember hydrogen in the collection. So if you're looking for basic standard state, that's how you know. At any rate, notice how the changes occur between the magnesium at 0 going to +2, and then hydrogen at +1 goes to 0. Okay, so +1 per element, then this goes to a 0 charge in that. But in these kind of reactions, you have to have balance of charge, and so we have diatomic here. We have 2 hydrogens, but we have 2. We're going from +1 to 0. That means you are gaining 1 electron, and going 0 to 2, you're losing 2 electrons. Like that. Well, you have to have a balance of charge, so I have to have 2 hydrogens, each gaining 1 electron, and that's what this is showing over here, 2 hydrogens which each gain 1 electron in this mix. And so magnesium is listed as is, and we go through and apply the rules and balance the equation. So that's what an oxidation reduction reaction. There are many of them. The other one is a metathesis reaction. This is also known as a double replacement reaction. What that means is there is no change in oxidation state, but the metathesis reaction has what we call a driving force in it that pulls it to completion, and that driving force leaves the system. The empirical form of a metathesis is AX plus BY goes to AY plus BX. And one of the reaction components, or the products, is the driving force. But if you look, A is now hooked up with Y, AY, and X hooks up with B. Like that. Now, metathesis reactions typically come in two forms. We call them salt-salt reactions and acid-base reactions. Usually the Arrhenius and the Bronsted-Lowry-Lewis theory is another thing. If I took, for example, sodium chloride and lead nitrate, like this, in aqueous medium, these are, I should put my terms in. You'll find these are typically in aqueous media when you apply them. Then you will notice that you can find the AX and BY in each of these. From complex ionic compounds like this, from left to right, the first metal, if you isolate it, everything behind that first metal is a polyion. So mentally, kind of make a line between that first metal and the rest of the molecule. And that's why I say it's very important that you understand what polyions are and how they hook up with the metals against the ionic nonmetals. Okay, so sodium is to connect with the nitrate, and lead is to connect with the chloride. And so we write those: sodium nitrate. We got to adjust a little, and then lead chloride. Like that. Now I did not put subscripts. The subscripts on the left do not necessarily mean that the subscripts on the right are the same values. Okay? The values of the subscript depend on putting compounds together in terms of the sum of charges equal 0 in the nature of writing compounds, especially ionic compounds in these equations. So sodium is a fixed charge +1, nitrate is a -1, so the sum of those is 0. So yeah, that's the correct ratio of elements in that compound. Over here, chloride's a fixed charge -1, it's in group 7, and lead is a +2. Well, that doesn't add up to 1, so that means, not a parenthesis on that. I have to put a subscript 2 on that one. I don't happen to have a chart. Maybe it's in the outline. Oh, it's in the Chem 1 outline, I believe. No, here it is. On your outline that I gave you, page 2 contains the driving force table. How to determine which of these two items on the product side are driving forces. And you have 3 parts to it. One is a solid precipitant, the one in the middle is a weak electrolyte, and the third is a gas decomposition, which comes from acid-base reactions. So which one of these two is an insoluble is what the question is. And if it is insoluble, then you say, okay, that is the driving force and pulls the reaction to completion. Well, if you look at the top table in this, well, let me say this: driving forces are 3 forms: solid precipitant, PPT, soluble weak electrolyte, or a gas decomp. Product. So one of these 3 will be over here, and there are cases I can show you where there's neither one of them are driving forces, and those are kind of the test questions that, well, which of these will not produce anything kind of outcome. So in order to determine which of those two are which one is the driving force, we have to use this table. Driving force is an insoluble from a salt-salt reaction. Again, driving force is an insoluble. So we're looking for insolubles. So if you read this table, this left side over here says solubles are these types of compounds except. And what does except mean? It means they're insoluble. So when we look at this compound right here, lead chloride, it is in the halogen group. And if the halogen, the chloride, is attached to one of the three elements here, then it's insoluble and yes, is a driving force. So since lead is in that category, the exception, yes, this, you can put an S out here as a solid, as a precipitant, and is the driving force. This table will be attached to your exam, so you can use it to predict the outcomes. How about nitrates? Is this a driving force or insoluble? If you look in the table up here, all nitrates are soluble, so therefore that is not a driving force. Now I have lectures online on these types of equations and how to pick out driving forces and balance them. I don't think I balanced the equation. There you go. Yeah. I need 2 over here. Yeah. So anyway, the outcome of this is dependent on you being able to read this table. All right, now that's the salt-salt reaction. The ones that we'll be using quite frequently, especially when we get to acid-base equilibrium, is acid-base metathesis reactions. In general, an acid plus a base gives a salt plus a weak electrolyte. Now, many people come to my class and think acid-base reaction produces salt and water, and that is true, but not always. There are reactions which you can mix together, and we'll show them to you in due time. I will pick an acid-base reaction that does water right now just to illustrate the metathesis, but you can have a double replacement that does not produce a salt, a weak electrolyte, water. Anyway, so let's look at, say, an HCl plus an NaOH, which is quite dominant in courses like this. It's a double replacement, AX and BY again. So we connect the outside elements or polyions, if the case may be, and write those down. So here's a sodium chloride, and I'm going to put it as an HOH. Now the way I've written this shows hydrogen kind of attached to the OH group, and this is what we refer to as an ionizable hydrogen. That means it has the potential of coming off, and you'll see this many times. This is the autoionization of water equation, in that I should write it like I wrote it up there. This hydrogen will pop off there and be an ionic form. Actually, it's a hydronium ion. Well, the simplified form. You don't have protons running around in solution by themselves anywhere. At any rate, what I'm showing you is AXBY, just like the AX and BY goes to AY. Well, that's BX in there. BX and AY, like that. So this is a acid-base reaction. Now, the water in itself is a weak acid. How do I know it's a weak acid? It is not a member of what we call the 6 strong acids. This you must learn. Memorize this. Apply yourself, please. I should have written them in columnar form. 3HClO4 and H2SO4. And this one is to the first ionization step. That means it ionizes in 2 steps, but only the first one is a strong acid ionization. What strong acid ionization means is these are 100% ionized. You will find no molecular forms of these compounds in solution. So when I say water is a weak electrolyte, it's because it's not a member of that collection of acids. Now again, the weak acids, as I'm showing you here, is illustrated in this diagram equation with what we call an ionizable hydrogen. Something like HC2H3O2 is acetic acid, and it has 2 forms of hydrogen in it. The hydrogen here is the ionizable, and the hydrogen's buried in the rest of the molecule, and in the same way we hypothetically isolate that first hydrogen away from the rest of the molecule, and this C2H3O2 is the acetate ion. And these are non-ionic hydrogens. Because they're bound into the structure so tightly, they resist ionization. Typically, ionizable hydrogens are attached to oxygen or a halogen. And HCl, HBr, HI, and that HF, as a matter of fact, is not one of the strong acids. HF, if you take the first halogen, is a weak acid because the issue is they do not ionize 100%. I might put that down. Weak acids do not ionize 100% as compared to the strong acids. Now, looking at the acetic acid, looks like this in structural form. So what I just said was the hydrogen attached to oxygen is your acidic hydrogen, or ionizable hydrogen, whereas the 3 attached to carbon are non-acidic. Bond's too strong to undergo separation in that by ionization mechanisms. We'll get to that in due time. Are many, you don't have to, this comes out of your Ebbing textbook in acid-base equilibrium. But here shows the way they've written these are many weak acids, and as you can see, all of them are prefixed by hydrogens out here, even though some of them have hydrogens buried in the polyionic structure. It is that hydrogen on the outside that undergoes the separation from the rest of the molecule and enters into the metathesis reactions, what I'm trying to teach you. Like in the salt salts, we had the ions, cation ions exchange places. here, ionizable hydrogen exchange places with the anion of whatever the base is in that type of system. So, with that little orientation, we go back to, say, acetic acid, HC2H3O2, in an aqueous medium plus sodium hydroxide in aqueous medium.
You're zoomed in pretty far.
I'm sorry. That's better. Okay. Acetic acid and sodium hydroxide. And so here is your A, X, and B, Y to take into consideration. And again, the exchange makes a sodium acetate, a salt, which remains in solution as aqueous, and the hydrogen hooks up with the OH again as a weak acid and has a liquid designation. And so the weak acid is the driving force. Now, this idea of the metathesis acid-base reaction will be an extensively used type of reaction as we go forward in the course, get deep into the course's structure and what have you, because of their importance in what we're doing. It's next to the last page or so forth. So if you'll open that up or just follow me as you go along, I'll take this one right here, iron chloride, and looks like sodium hydroxide. We'll run through that one real quick and talk about some other kinds of reactions that come out of this, the ionic equation and the net ionic equation. So we have iron chloride, that'll be in solution, and sodium hydroxide in solution. What are the products of that? The outcome of this, again, depends on you recognizing the cation-anion exchange, the AX and BY. Here's the hydroxides, the polyion, but the first metal is your cation and everything else behind it is the anion. So we'll have an exchange between iron and hydroxide and sodium and chloride. Now you recall when you exchange something like sodium and chloride, you do not bring the subscript over. The subscript over here is 2 because iron is a +2 charge. But over here it's going to have it's going to be hooking up with something that has a +1 charge, the sodium. And when you add those oxidation states, you get 0, so that's the appropriate formula for sodium chloride in that one. And then you have iron hydroxide coming together, and if you know your polyions, that is a -1 charge, and iron has a +2 charge because it has a +2 over here. Remember what I said about metathesis, the oxidation states do not change. So I will have to, if the OH is a -1, I will have to have 2 of those to give me a -2 to cancel out the +2, and that's your proper form. Now, which one's the driving force is a solid precipitant. So we go to our salt ionic compounds up here, and we find the hydroxide collection. All hydroxides now are in this column are insoluble and driving forces unless you have a group 1 ammonium, barium, or strontium. Well, neither one of those. So we can say that iron is a precipitant and driving force for that reaction. This one remains in solution aqueous. All halides are soluble except mercury, silver, and lead. I call them the happy halides, HAP, mercury, silver, and lead. At any rate, that's a molecular equation in the classification world. You put in terminology with this. Make some room up here. Now, it's frequently needed in the ionic form. Ionic equations. In writing these ionic equations, everything is written in ionic form except weak electrolytes and driving forces. Now, weak electrolytes refer to weak acids and weak bases. And driving force, of course, it can be a precipitant or another weak acid formed out of the reaction. So, when we take the metathesis reaction up here, we look for weak acids on the reactant side. Well, there are none. The strong bases are group 1, group 2 hydroxides, except for beryllium. But the iron chloride ionizes, and they're all aqueous. I'm going to goes to that. See how it has 2 chlorides and 1 iron, so what you do is write it in that format. And then sodium hydroxide breaks up into the sodium ion, the hydroxide ion. They're all in aqueous, and then that produces a sodium ion and chloride ion. And none of those fit this weak electrolyte or driving force, but the iron hydroxide is a driving force, so we would not show it in ionized form. And we might note that as a S on the end to indicate solid on that. Now, one other, this is ionic equations. Now there's one more that you need in these is net ionic equations. If you look at the ionic equation, you'll see sodium and chloride. I need it actually to balance the equation. I should have had 2 and 2 right there. Sorry. Like that, you'll notice that, well, let me go back up here and balance the thing. I got 2 chlorides, so I have to have that 2, yeah. So that would be 2 also right there. Okay. So if you look at the left side and the right side, you see sodium and chloride on the left, sodium and chloride ions on the right. Those are called spectator ions. And we can they are important counter ions to carry whatever's reacting in the reaction, but they can be eliminated to show only those components that are reacting. And that leaves iron and hydroxide, actually 2 of them. What did I? Oh, I should have put it there, not here. That's already, that's right. 2 hydroxides. Chlorides fall out, 2 hydroxides, and that goes to iron hydroxide. There we go. Yes, so these remain aqueous. And this is your net ionic equation. And many problems will need you to work right down to that particular expression and use that in trying to solve another problem element or whatever in the issues. Okay, then. Now, the other classifications of oxidation reduction reactions include composition decomposition reactions, and single replacement. All of these are oxidation reduction type reactions. Oh, one more, combustion reactions. Hydrocarbon combustion, that is. You can have combustion reactions in many of the element families, but we will work only with hydrocarbons and stuff. So now these are essentially the same set in that decomposition is just the opposite of composition. Now, to help you memorize the decomposition reactions, you can see on the outline that I gave, on the worksheet, sorry, that I constructed an acronym that can help you remember these types of. So if we go COACHE, you can follow me on the list. You can see carbonates, oxides of metals, acids. These are mineral acids. Chlorates. Now, this is called an analogous series. Similar series, because if you use chlorine, this just fits the acronym, chlorates, but there's also bromates and iodates out of the halogen selection. Hydroxides, derivatives, and this is a process, electrolysis. This is the refining of salt solutions or salts into their basic standard states. This is electroplating. Anyway, the idea is that carbonates, if heated, break down into non-metallic oxides and sometimes water. So you can look on there and you can see the metal oxides and non-metallic oxides are your primaries. If you take calcium carbonate, heat it, you'll get a calcium oxide and a carbon dioxide. Whereas you go to the acids up here, the oxides, not acids, oxides of metals, the iron oxide, this is rust, and heat it, Fe2O3, you'll get iron in a solid form, plus O2 will come out of that. And so these are the outcomes of this Coach E acronym. And so we need a 2 there, let's see, I have a 2, and a 3, 2, change that to a 4. So you'll be able to do that. Acids. Now, if we took, H2SO3, so ferrous acids, not H2SO4, and heated that, you'd get a non-metallic oxide. It steps down one oxygen, SO2 gas, and it goes to water as a liquid. And then if you step down from let's see, the next one is the chlorate. A chlorate is something like potassium ClO3. That's a potassium chlorate as a solid. If you heat this, it goes to salt, ClO, as a solid, plus oxygen, O2 as a gas, 3, 2, and 2. Now, I'm leaving it to you to study this. This is Chem 1 stuff. Now, I'm just reviewing some topics and refreshing them. That's why I'm going so fast. I'm making a lot of detail out of this. So if you're weak in this, please invest your time in study and memorize these, and go back, and I've got videos online in Chem 1 on decomposition, reactions, and all of it. So you can go in there and get a great deal of detail on how these are put together. But you also have bromates. If you say you had a sodium BrO3 NaBrO3 is a solid. It does the same thing. It goes to a sodium bromide as a solid, and it would also kick out oxygen in that same way, 3, 2, and 2. And delta symbol means you're heating it, like that. Iodate does the same thing. Hydroxides, if you had a calcium hydroxide heated, that's a aqueous solution or solid if you want it. It'll break down into a metallic oxide and water, like that. And this is a -2 + 2, that's correct. Liquid, and that's a solid. Maybe it looks like a solid in there anyway. Okay, so what's the last one? Electrolysis. Okay, is the refining of salts. With electric current. It says current right there. Yeah. With electric current. Electrolysis you will learn about deep into the course on electrochemistry, but it comes in two forms: melt electrolysis and aqueous. So salts dissolve in water to a certain extent. And the easiest one to kind of comprehend is the melt electrolysis, say for potassium or something like that, potassium chloride. And you have a reservoir with melt potassium chloride, melt salt, and we'll use potassium chloride. So when that breaks down, it goes to potassium and chloride ions. So you've got all these mobile potassium ions and chloride ions in the system. Okay, in this heater jacket. Then you put electrodes into the solution. Let me make that a little shorter. And connect those electrodes to a transformer like that, minus plus. And so the minus charge makes this electrode negative, and the plus side of the battery or transformer makes this one positive. So opposites attract. So potassium goes there, chloride goes there. Okay. Now, when potassium goes, it's lacking an electron, so it'll gain an electron and go to potassium neutral. Chloride has an extra electron, so what it does is it goes to see, actually two of these are needed. It goes to two electrons. So this is reduction. This is oxidation taking place within the electrolytic cell. And these are pure forms of or basic standard state forms that are generated out of that running the electric current through that salt solution. We'll get to that in great detail as we get into electrochemistry down the road. But in all of these reactions, there's a change in oxidation state. Let's see. Let's take the Fe2O3. This good old down home rust. As a solid goes to iron as a solid plus O2 as a gas, and that's a 3. I need a 2 here and a 4 here. But when you look at these elements, oxygen is always a -2 unless I tell you otherwise. Write that down on the sidebar. Oxygen is always a -2 and hydrogen is always a +1 unless I tell you different right now. So this is a -2 and iron has to be a +3. Iron 3. And so 2 to 3 is a -6 total, and 2 to 3 is a +6. So these will cancel each other out, go to 0, so that's the proper formula for that. Over here, these are given to be 0 because they're basic standard state elements. How do you know they're basic standard state? Well, there's a table in the back of the book to list all the compounds and elements and stuff. Any element that has a 0 delta HF is a basic standard state. I'll show you that. Won't take me a second. See if I can find one. There's one. This is a table of thermodynamic properties. At the top, you'll see these symbols. Real quick. This is called the heat of formation. Now, substances have heats of formation with them. Okay, just by itself, bromide going into the gas phase absorbs 111.9 kilojoules of energy going from say ground state up to, well, from solid state up to say a gas state, whatever. Down here you see Br2 is a 0. If you find a 0 under delta HF, that's the basic standard state of that element. You can go down through here. There's calcium right here. That's the basic standard state of that one. And you keep going. Graphite, that's carbon. We'll use that a lot. That's basic standard state. So, but compounds all have numbers by them. That means they are formed from basic standard state elements, but they give off or absorb energy depending on what you're working with. But the issue is that's where you get the oxidation state of 0 because they're neutral elements in their basic standard state, all of them. At any rate, when you look at ion changes from a +3 to a 0, this is a gain of 3 electrons. And going from oxygen -2 to 0, this lost 2 electrons. And so you proceed to balance it. But the issue is there's a gain of electrons and a loss of electrons. You really don't lose them, obviously. But those that are lost by one element are gained by another. And you have to have a balance of charge in the overall process. I'll show you some very simple ones right now. I'm sorry. There we go. So to repeat that, iron starts at +3 and goes to 0, -2 to 0, and so the issue is it's an oxidation reduction reaction because the elements within that reaction undergo changes in oxidation state. These have an empirical form. A plus Bx goes to Ax plus B, and is an oxidation reduction. Notice that A replaces B and forms the product Ax, and B is sometimes called a leaving group. At any rate, this is based upon what we call the activity series. Predicting the outcome of a single replacement. So in your handout on your equations, page 2, you get this one right here. Turn to page 2. There's your activity series right there. And the way you interpret this is whatever's at the top will replace anything below it. So if you have A would be above B in this activity series, whatever you choose in the single replacement. So A is above B in activity series. If, when you write the reaction, if B is shown to be above in the reaction first, trying to replace A, you say no reaction occurs. We'll take zinc, basic standard state, and copper, say sulfate. Aqueous, what's the outcome of this? Well, if you look at the, let me get up here. You look at the activity series, we can find zinc is right here, and copper is here. So that arrow on the left shows that whatever's up here will actively replace something below it. As in the textbooks, they define this as a more active metal replacing a less active metal. Another way to look at that is zinc prefers to be connected to SO4 more than copper does. So either way, whatever helps to kind of understand the concept. But this goes to zinc sulfate plus copper in its solid form, like that. And if you look at this, this is a 0 oxidation state. Sulfate's a -2, copper's +2. This was -2, this is +2, and this goes to 0. So zinc goes from 0 to +2, copper goes from +2 to 0. And so you see a gain, lost 2 electrons here, and this one gains 2 electrons. Now, it's an oxidation reduction. The process of gaining electrons is the reduction process, and losing the electrons is the oxidation. It's easy to remember this in the acronym OILRIG. Oxidation is loss, reduction is gain. So you can remember those pretty easily when you start working with these. Now, balancing oxidation reduction reaction, I'm sitting there thinking, probably better be served when we get to electrical chemistry. That's where we'll be using it. And if anything's needed before then, I'll just fill in the blanks as we go. And it's just simply always yields, the combustion of hydrocarbons always yields CO2 and water. Hydrocarbon plus O2 in that written form indicates the presence of that O2. This indicates combustion. When you put oxygen with the hydrocarbon, and gives CO2 and H2O. And of course, you balance it based on whatever hydrocarbon you have. Methane, for example, plus O2 gas gives what? Well, it's a no-brainer. It's CO2 and water. And gas, and you can put this as gas and water in gas form or liquid form, doesn't matter. Steam or liquid condensate. Like that. Now balance the equation, carbon, carbon. Save your elements that are by themselves to last in balancing any equation. 4, and so we need a 2 there, so that leaves us 1, 2, 3, 4, 2 there, and so this is your balanced combustion reaction in the basic standard form. So if I have C2H4 as a gas plus O2 gas as a combustion reaction, what's the outcome? Well, again, it's a no-brainer. And then you balance your equation. So whatever the hydrocarbon is out here, if it's attached to O2 in this context, just put CO2 and water as the yield of it. And we'll be using those frequently in some of the work we do. We've got 2 carbons and we need a 2 there, 4 hydrogens, Either 2 there, so 2 and 2 is 4, 5, 6, so I guess I can do 3 right there. And so that's pretty much the cross-section of and background of equations. Now, it is up to you to go through this worksheet and develop your skills. You will see the elements of this show up in many places as we go through Chem 2. And so, to your advantage, please invest wisely. Okay, let's take about 10 minutes and then we'll